At this point, you should be able to tell a strong acid from a weak acid, but we still haven't said anything about what their relative strengths might be. For this purpose, we need to define something called the pH. So our learning goals for this video are to define pH and then to describe exactly what it means in terms of acid strength. So for strengths of acids, I think a common sense intuitive notion is that it must be related to the concentration of the hydronium ion in the solution. If we can find some way of specifying that, we can say something definitive about acid strength. Now, strong acids are going to be directly related to the concentration of the acid in water, for example, because they completely dissociate, so whatever the concentration of the acid is, that's pretty much what the concentration of the hydronium ion is going to be. But in the case of weak acids, there's an acid dissociation equilibrium, and that's what really determines the strength or the concentration of the hydronium ion in solution. Now, as we go through this, there's going to be an important side equilibrium that we need to be aware of, and that's the equilibrium associated with water ionization, autoionization. Now, that's this process where water can spontaneously dissociate into hydronium ion and hydroxide ions. Now, it doesn't happen in large quantities, but it does happen to some extent. It has an equilibrium constant of 10 to the minus 14. Now, remember, I don't include water as a pure liquid in my equilibrium expression, so I only have the concentration of hydronium ion times the concentration of hydroxide ion. Now, this one's pretty easy to solve for those concentrations. In fact, I would find that each of those has a concentration of 10 to the minus 7 molar. But that's not zero. And this is something that's going to be very important as we work through some of the equilibria that we're going to be talking about in this module. In most cases, we're going to run into solutions that have a hydronium ion concentration that has a maximum of about 1,000 and a minimum that could be as low as 10 to the minus 18 or even lower. Now that's 21 orders of magnitude. That's quite a large range of numbers, and so talking about them in a convenient way is the challenge that we face now when we talk about acid strengths. For this purpose, we devised something called the pH scale. Now, I want to illustrate this with a little bit of an example. Let's suppose we have a solution where the hydronium ion has a concentration of 10 to the minus 5 molar. So if I write that out in decimal form, it's going to be 0.00001 molar. And what I want to know is there an easier way to describe this? Now, I think of this a little bit like colloquial language. We use a code when we talk. For example, when I'm meeting somebody I know well, I don't go up and say, "Hello, how are you today?" No, I might say, "Hey, what's up?" Or even in more modern language, I might just say, "Sup?" All right, I'm going to use something shorter to express myself because we tend to like short, convenient ways of talking. So when I talk about a hydronium ion concentration of 10 to the minus 5, do I really want to say, well, the hydronium ion concentration is 1 times 10 to the minus 5 molar? No, I want to find something easy to say. So I might just focus on that exponent and say, it's got a strength of minus 5. Or better yet, what if I just use 5? Well, it turns out that's exactly what chemists do. Chemists are really lazy. We don't want to say 1 times 10 to the minus 5. We want to just say 5. So we define this to be the power of hydrogen, or pH. So our formal definition of pH is just going to be this, that the hydronium ion concentration is equal to 10 raised to the minus pH power. So all we have to do, in essence, is look at the concentration of hydronium ion, look at the exponent of 10, and that tells us something. That tells us what the pH is going to be. Now, mathematically, that actually is equivalent to this, that pH is equal to the negative log base 10 of the hydronium ion concentration. But I got to tell you, a lot of people freak out when they see this definition because we aren't as used to using logs mathematically, so this looks very strange. But let's just interpret that. I mean, this is a foreign language class, right? I'm teaching you chemistry language. So if y is equal to 10 to the x, then the equivalent way of expressing that using logarithms is to say that log base 10 of y is equal to x. Now, how do we draw the correspondence here? Well, I look at the 10 there, and that's just telling me the base. That's telling me the number to which this exponent is going to be raised. And the exponent is the thing on the right side of this, the x. So this is telling me directly, when I see log base 10 of y equals x, that's telling me that 10 to the x equals y. These are equivalent statements. This is the definition, though, that we're going to be using throughout the course, and so I'm going to try to use this as much as possible when I'm describing things involving the strength of acids, because I think it's just a little bit easier for us to grasp. It's a little bit closer to our common experience. Now let's see what this means in terms of acid strength. Let's suppose we're going to look at a range of different possible acid concentrations, hydronium ion concentrations. Now I can write them out as exponents of 10. If you want to see them in decimal form, they look something like this. Sometimes it's easier for us to grasp the relative magnitudes of things when we write it out as a decimal. Now, I can easily convert these things to pH. So, for example, the first one is 10 raised to the minus 1, so the pH has got to be 1. The second one is 10 to the minus 3, so the pH is 3. This goes on in the same trend, so the last two are 6 and 10. You can see that it's much easier to say, well, it has a pH of 1. Instead of saying it has a hydronium ion concentration of 0.1. All right, so we're going to use pH to describe this. Now, which one of these is the strongest? When we look at the decimal representation, it's pretty easy to see that the strongest one, the one that has the highest hydronium ion concentration, is the one on the far left. That is the strongest. And the weakest is going to be the one on the far right, because it's got all those zeros before we get to 1. All right. This is going to be a little bit counterintuitive with pH, because the smaller the pH, the higher the concentration of the hydronium ions. So small pH numbers means lots of hydronium ions. Very large pH numbers means very few hydronium ions. So we have to get used to thinking in terms of large pH means not very acidic, and small pH means actually extremely acidic. This includes negative numbers. You can have negative pHs. They correspond to hydronium ion concentrations that are 10 to the 1 or 10 to the 2, for example. Now, to get you acquainted with what this means in terms of real stuff, here's a pH chart that runs from 1 to 14, and it shows you different things that you may have run across in everyday life that have these different pHs. I want to call your attention, though, to the very middle where it says pure water. That's right, pure water has a pH of 7. That's something that we learned on the earlier slide when we said that the concentration of the hydronium ion was 10 to the minus 7. That is a pH of 7. So implicitly what all this means is that when something has a pH less than 7, it's acidic. And when it has a pH greater than 7, it's basic. So if you can keep this general idea in mind, you'll be able to do just fine in terms of interpreting what the various values of the pH mean.